This is Chapter 8, Example Problem 3. Once again, we are designing some type of circuit. In particular, this circuit multiplies a single 8-bit input by 3, and what the problem states is the resulting output is always correct. And so what we have here for this circuit is circuit, I should probably give them better names, but we're okay for now. We'll just call it A. It's 8-bit. And here's the output. The notion here is how wide this is going to be. And this is very much the same as the last problem. If I add two 8-bit numbers, it's the same thing as multiplying by 2. This problem specifies a multiply by 3, which means I don't know how to multiply in digital design. So what I'm going to do is add that input value 3 times. If I add it 3 times, if I add two 8-bit numbers, it could be a 9-bit number. If I add another value, it could be a 10-bit number. And so we did the math on that before, where we had 4. This is from the previous problem. 4 input values that we're adding. 4 equals 2 squared. They're 8-bit values. 4 times 2 eighths, it was 2 to the 10th. We don't need all 4 values, but we do need the 10 bits to make sure this answer is always valid. So once again, this is going to be a 10 there. So we're going to, once again in this problem, we don't know how to multiply, so what we're going to do is add. So we can start off by adding. Oh, the only way we know how to add is ripple carry adder. And this carry out is essentially the 9th bit. And so what I need to do is retain that, and what I'm going to do is append that to this bundle here, and I'll put a note here. And looking good. So next problem here is I need to add A one more time, and I have once again a ripple carry adder. To make it 9 bits to make this other ripple carry adder happy. And what I'm going to do, this is my little append notation. I'm going to say 0. This is 8 bits. Comes 9-bit 0. So these are unsigned numbers. I'm just going to add an extra 0 on the left side. It suddenly becomes 9 bits. Makes this ripple carry adder happy because now both inputs are 9 bits, and I know I'm running out of room here, so I'm going to say sum, and we'll say carry out. This is really terrible because I ran out of room, but we need to append that carry out to the sum. The sum is now 10 bits, and we'll say, so once again we appended a 0 in this condition. We did 2 more append operators there. We appended the carryout to the sum, which made it valid. So this problem, the output's always going to be valid because we extended the bit width as we went along. This problem, once again, we're using ripple carry adders. They have no control inputs, so we're going to call this once again no control.